Welcome to my YouTube channel. So, in the previous lecture of complex numbers, I have discussed about complex numbers and representation and some properties. So, now today, lecture 2, I will discuss one theory and some examples. So, first of all, what is totally ordered? Totally ordered set. R is totally ordered. This means for any two elements of R, if A not equal to B, then either A greater than B or A less than B. This means that this R is totally ordered. Okay. Any two element from this R, if they are not equal, then there must be either of one. But in complex number, this property does not hold. So there is a theory, the field C cannot be totally ordered in consistence with the usual order on R. So we prove this theorem that this field cannot be totally ordered in consistence with the usual order on R. So as R is totally ordered, in the same way the set of complex number cannot be totally ordered. So to prove this, first we suppose that C is totally ordered, that is, suppose that such an total ordering exists on C. Then for I belongs to C, we would have either I greater than 0 or I less than 0, since I is not equal to 0. So as I is not equal to 0, that is A not equal to B, then A greater than B or A less than B happens. This means in either case that is minus 1 equal to I square can be written as I into I, or can be written as minus I into minus I. So this is greater than 0 by this property. So as I not equal to 0, I will be greater than 0 or I become less than 0. So if we consider this case, so I square, we know this value is minus 1. So this will be greater than 0 if we consider this, but this is a contradiction as minus 1 greater than 0. So this is not true. So such and total order is impossible in this set of complex numbers. So you can note this theorem means that Z1 less than Z2 or Z1 greater than Z2 have no meanings unless they are real. So if they are real Z1 Z2, then there is a meaning of the relation between these two elements Z1 less than this. But if they are complex, so we cannot write in this manner. So between two element of complex numbers, we cannot compare as greater than or less than. Now we discuss modulus. Modulus or absolute value. So the modulus or absolute value for x belongs to R is defined by modulus x equal to x if x greater equal to 0 and minus x if x less than 0. As C is not totally ordered, so there is no condition such this. So in complex number there is no such definition for modulus, but we denote the modulus value of z equal to x plus iy in set of complex number as mod z equal to root over z into z bar, that is complex conjugate, and this becomes like this, x square plus y square, and this is the, if this is z xy, mod z imply the length of this vector, that is length from this point to the origin. This modulus means this. So there is some property like real z, modulus real z less or equal to mod z, and also imaginary z modulus of imaginary z less or equal to modulus z. Also we can write z1 by z2. Modulus of this value can be written as mod z divided by mod z1 by z2. And also we will use some properties like real z1 plus z2 equal to real z1 plus real z2, and the same property holds for imaginary also, that is z1 plus z2 equal to imaginary z1 plus imaginary z2. So like this, so we will use this and also this in the next examples or problems. So let's see. So now we prove these problems. So one is modulus z1 plus z2 less or equal to mod z1 plus mod z2, that is triangular inequality, equivalent inequality, this. So first we prove 1, and using 1 we prove 2. To prove this, we observe that if z1 plus z2 equal to 0, then there is nothing to prove. So as z1 equal to 0, then this equal to 0, so 0 less than this. So now we consider when z1 plus z2 not equal to 0, so then modulus z1 plus z2 not equal to 0. Since real z less or equal to mod z, so we can write modulus z1 by z1 plus z2 plus modulus z2 by z1 plus z2. For z1 z2 belongs to C, this greater equal to real, this number z1 plus z2, and this is also real z2 divided by z1 plus z2. So this becomes 1. So from this now we put this as mod z1 divided by mod z1 plus z2 using the property of modulus, and this becomes this z1 plus z2 is equal to 1. So from this we get, so this here not equal, so this becomes greater equal to, so this becomes here, so z1 plus z2 goes here, and this is lesser equal to, and this becomes z1 plus z2. So this is the proof. So now using this we will prove second part. So this problem 1 can also be proved in another way. It is like z1 plus z2 whole square can be written as z1 plus z2 into z1 plus z2 bar, as mod z whole square equal to z into z bar. So from the this becomes z1 z2, and from here we get z1 bar whole square, this into this, and from this into this we get z2 whole square, and from this into this into this, and this into this we get 2 into real z1 z2 bar, and from this we get z1 square z2 square, and this becomes 2 into modulus z1 z2 bar, as real z lesser equal to modulus z. So from this we can write z1 whole square plus z2 square, that is modulus, and this becomes 2 mod z1 mod z2, and from this lesser equal to we can write z1 plus z2 whole square. So this can be written as z1 plus z2 lesser equal to z1 plus z2. So in general way we can write this as modulus summation z equal to 1 to n lesser equal to summation z equal to 1 to n modulus z equal to 1 to. So this is for j equal to 1 and 2 only, and here for j equal to 1 to n. So this is the proof, and this is triangular inequality explained by geometrically. So now we prove second problem. For second problem, first we take z1 equal to z2 plus z1 minus z2, so this becomes z1. So now we find z1, so this becomes this z2 plus z1 minus z2. So now we take this as z1 and this is as z2, and we use the first problem, then we get from here lesser equal to modulus z2 plus modulus z1 minus z2. So then we get, if we terms here. So that is z1 minus modulus z2 less or equal to z1 minus z2. And in similar way, if we take z2 equal to z1 plus z2 minus z1, then we get modulus z2 minus modulus z1 less or equal to z2 minus z1. So if we write it as 1 and this is 2, so from 1 and 2, that is combining 1 and 2, we get, so this is z1 minus z2 and this is z2 minus z1. So we can write mod of modulus z1 minus modulus z2, and this is less or equal to z1 minus z2. This is problem 2. So we proved it. So triangular inequality, you can note down. So now we graphically explain this triangular inequality. So for this, if this is modulus z1 and this is modulus z2, as this goes to this, so this will be z2 and this will be z1 plus z2 modulus. So as we have sum of any two sides of a triangular is greater than the length of third side, so from this we can write, so sum of this z1 and z2 is greater equal to length of the third side. So this is exactly the triangular inequality. So this, if this is z1 and this is z2, so the length modulus z1 modulus z2, and as this is a vector, so parallel of this we can write this. So and by vector law, if this z1 and this z2, so this becomes z1 plus z2. So from this we can verify the length triangular inequality. Similarly, we discuss the complex number x plus iy and complex number x minus iy, and from this is minus z equal to minus x minus iy. So if this is x, that is x comma y, x, this is y, so this vector is z, so the z bar will be x minus y. So this is x and this is minus y. So this will be the mod z and this will be the mod z bar length, and the negative value, that is minus x minus y, exactly opposite here. So this will be minus x minus y. So this will be the also minus this and can be this. So this is the graphical representation of z bar minus z. So from here we can conclude that the z bar is the mirror image of z with respect to the real axis, and minus z is the mirror image of z with respect to origin. So from this we can conclude that z bar is the mirror image of z with respect to real axis, this, and minus z equal to mirror image of z with respect to the origin. So for today, that's it. If you like it, please do subscribe and share with your friends. For the students of IIIT Bhagalpur, it will be very beneficial. I will cover all the module and the previous year question. So please share with your friends. Let them know that I have started the complex numbers, the course you are dealing with, that is MA 201 subject code. So I will cover this. So do subscribe and please click on the bell icon. Thank you very much. We'll talk in the next lecture with more examples and more theory. So thank you very much. Dhanyawad.